Hello. Lecture 24 of Applied Statistics finally moves on from the difficulties and the intricacies of regression and multiple regression to something that's actually easier, chi-squared goodness of fit tests, and also chi-squared tests for independence. For my students at Bethel, we're in this book. We're moving on to chapter 15 of the book from chapter 12, so we're skipping some chapters. And here's the lecture plan. We're going to illustrate these two tests through examples. I'm not really going to do the abstract theory in a ton of depth. First, we'll look at a chi-squared goodness of fit test, and the example I'll talk about is free throw shooting. In fact, my free throw shooting, which is pretty bad, but it will suffice for the purposes of illustration. First, we'll do a z-test to test the population proportion, which really represents my probability of success on any given free throw. But then we'll generalize that. We'll look at the overall distribution when the number of attempts is fixed. I'm going to talk about taking 4 free throws at a time and counting how many successes I have, which is a binomial random variable, and I can either have 0, 1, 2, 3, or 4 successes. Can we test that overall distribution, and is that a different test than testing the probability of success on any one attempt? Yes. Based on running experiments, in other words, taking 4 free throws, counting how many successes I have, and doing that over and over and over again, we can test the overall distribution using something called a chi-squared statistic with a certain number of degrees of freedom. How do you compute the chi-squared statistic and compute the p-value? We'll talk about that as well. The other situation is for testing independence of 2 categorical variables. We'll do an example there as well. We'll make a table, a two-way table of observed counts for these 2 variables, these 2 categorical variables that have different levels. We'll also look at the two-way table of what are called expected counts if we assume these 2 categorical variables are independent, unrelated, not associated. We'll compute, once again, a chi-squared statistic with a certain number of degrees of freedom. The way you compute the degrees of freedom in these 2 different situations is different. Finally, we'll compute the chi-squared statistic again and compute the p-value, and in both situations we'll decide whether to reject the null hypothesis or not and think about the real-life implications. So here's my example, free throw example. My in the driveway free throw percentage, and okay, so when I say in the driveway, I mean I actually have a basketball hoop in my driveway and I try shooting free throws at approximately the right distance, but I'm very bad, okay? I'm terrible at free throw shooting, and my probability that I've kept track of reasonably well over the years is about a 40% free throw shooter. Now that's bad, right? Good is maybe 60, 70% at least. A really good free throw shooter is 80 or 90%. I'm really bad. I'm okay at passing and dribbling, but I'm a terrible free throw shooter. I'm a terrible shooter in general. I just don't understand how people get so good at shooting sometimes. But am I really a 40% free throw shooter? We could try to test that. We could do a hypothesis test where the null hypothesis would be P, my probability of success on any one attempt, which would also be my proportion of successes over many attempts, is 0.4, and an alternative hypothesis that it's not 0.4. We can do a two-tailed test, or we could do a one-tailed test as well, but let's do a two-tailed test. So I'm testing the null hypothesis that p is 0.40 versus the alternative hypothesis that p is not 0.40. And suppose I choose to attempt 400 free throws to test this. Okay, with somebody feeding me the ball so I don't get too tired, right? Because if I was chasing the ball every time, this might take an hour or two. I'd get really tired, and that could affect how well I do. So hopefully if they're feeding me the ball, I don't get too tired. My probability of success stays reasonably constant. Let's suppose, for the sake of argument, that I have 150 successes. So that would be a 37.5% success rate for my sample. This would be a sample proportion of 0.375. Question is, will we reject the null hypothesis? So we have to compute the test statistic and the p-value, right? We need to see whether these data are extreme or not when the null is true. Could they have occurred reasonably well, at a reasonably high probability by chance? That's what the p-value is telling us. If we get a small probability, a small p-value, then we say we have observed something extreme when the null is true, and so we reject the null, and we think it's not true. So here's the test stat and the p-value for this made-up data here. Z is about negative 0.102, so the p-hat here, again, that's my sample proportion, that's the 0.375, 37.5% is 150 divided by 400. The null value, again, is 0.40. You also divide by the square root of the null value times 1 minus the null value divided by the sample size. You can check on your calculator. This comes out to about negative 1.02. Hopefully I have not made a mistake. It's possible I do make mistakes, so check things after me. And that results in a two-tailed p-value of 2 times this probability right there from the standard normal distribution, which ends up being about 31%. Not small enough to reject. So we fail to reject the null hypothesis. I do not have evidence against the null. Instead of saying accept the null, it's typically better, I think, to say fail to reject. We just don't have enough evidence against the null when we give the null the benefit of the doubt. I mean, if you think about it, especially with two-tailed tests, the probability or the chances, you might say, the betting odds of the null being true is basically 0. Although you really can't assess that probability accurately. But I mean, you're saying p equals 0.40 exactly? Well, probably not, but we're giving it the benefit of the doubt. That's always the perspective to have with hypothesis testing. All right, on to page 2. Another approach that tests something related, but definitely not the same thing. Okay, so I'm about to do a different test, a chi-squared goodness of fit test, whatever that means. That's going to test something related but not exactly the same. What would happen if I took my 400 attempts where I keep track, it's either success or failure for each of those 400 attempts, and I break down into 100 random experiments of 4 free throws each. In other words, my first 4 free throws, my second set of 4, which brings me up to 8, my third set of 4, which brings me up to 12. I mean, it would make the most logical sense to do that in order, though in reality, I could break it down with any groups of 4 at random even, to do this test. But I'm thinking of it in terms of the initial 4, the next 4, the next 4, etc. I'd have 100 of those random experiments. And in each situation, I could let capital X be the number of free throws that I make in these 4 trials in each experiment. So that can be either 0, 1, 2, or 3, 0, 1, 2, 3, or 4, 5 possibilities. The claimed probability distribution for X then would be a binomial distribution. This is a binomial random variable, a very famous kind of random variable with a probability of success equal to 0.4 if the null's true. And the resulting probability distribution can be found by computing these binomial probabilities using the formula for probability density function, or if you prefer, probability mass function of a binomial involving binomial coefficients. Here would be the answer. You may want to pause the video to double check these things. The probability that I make 0 would be 0.1296. The probability that I make 1 would be 0.3456, as well as the probability of making 2. The probability of making 3 is about 15.36%, and the probability that I make all 4 is about 2.56%. Okay, so again, I'm a bad free throw shooter, so I'm more likely to make fewer than a higher number. All right, so that would be my distribution in 4 attempts of how many that I make. Okay, so now I'm really, in this chi-square goodness of fit test, I'm really testing this overall distribution rather than just the probability of success, p equals 0.4. That really is testing something different, though of course related. Now let's be more careful in how we look at the null and alternative hypotheses in a way that'll generalize. For these 100 random experiments of 4 free throws each, let x sub I be the number of times that I made I free throws, where I can be 0, 1, 2, 3, or 4. Okay, so again, I'm doing this 100 times. These x's that are going to be x0, x1, x2, x3, and x4, 5 of those, have to have values that add up to 100, because I'm doing this experiment 100 times. If the binomial model from the previous slide is accurate, then the 5-dimensional random vector that I make by putting all these x's together like this has a name. It's said to have a multinomial distribution. It's a multinomial random variable. It's a generalization of a binomial. It's got parameters, first of all, n equals 100, because I'm doing this experiment 100 times, which again corresponds to 400 total free throws. P0 is the probability on any one experiment of those 100 that x0 occurs. In other words, I make 0 free throws. P1 is the probability that I make 1 free throw. P2 is the probability that I make 2. P3 is the probability that I make 3. And P4 is the probability that I make 4, if the model is accurate on any one time. Based on the observed values of x, then we can proceed to do the following hypothesis test. The null hypothesis has 5 parts to it. P0 is 0.1296, P1 is 0.3456, etc. And the alternative hypothesis is that Pi is not as stated, It's not equal to these for some, at least one of those i's, 0, 1, 2, 3, or 4. Once again, we emphasize that you're giving the null the benefit of the doubt. In the big scheme of things, you might say the null has no chance of being exactly true. But remember, you're giving it the benefit of the doubt, so you're only looking to see if you've got evidence against it that's strong enough to reject it. This is technically a different test than the z-test from page 1, 2 pages ago. This is page 3 of this example here. Okay, it is a different kind of test. There we were testing, is p 0.4, where p was the probability of success on any one time I'm taking a free throw. Here I'm looking at the overall distribution in 4 attempts. We should expect a different p-value, okay? But what is the test statistic? It's no longer z, it's chi-squared. Here's a theorem, though I put the word theorem in quotes because it's not actually a theorem. It's got some vague language in it. Theorems have to be very precise. It might be better to call this a result. Here it is. Let capital X be a vector random variable. Notice I'm using different subscripts here. It made sense to start the subscripts for my example at x0 because I could make 0 free throws in 4 attempts. But here in the general situation, we're starting at x1 and going through xk. My example, x0 through x4, that is 5 conditions. I could have labeled them x1 through x5 to match what you see here in this result, but again, it made more sense because I could make 0 free throws. That's a multinomial random variable with these parameters. For large n, is 100 large? Well, there is some guidance in our textbook for my students. I'll let them decide whether in a given situation n is large enough. The following random variable follows approximately a chi-squared distribution with k minus 1 degrees of freedom. Okay? What makes this not a theorem? What makes this vague? Well, the word large is vague and the word approximately is vague. That's why it's not a theorem as stated. Okay, you have to make things more precise. Here is the notation for the chi-squared random variable, though I will tell you that oftentimes we write this to look like an actual x, a solid capital X. But I did want to emphasize the Greek letter here, so I made it more like a lowercase chi. Chi-squared is this summation that you see here. What is the summation representing? Well, each term in the summation is representing, well, first of all, a fraction. The numerator is a value of the xi, like x1 for example, minus n times the corresponding pi. Think about what that means. I'll say it here in a minute, but think about what that means. Quantity squared divided by npi. What is npi? npi is really an expected value. You can call it ei for expected value. What is it the expected value of? It's the expected value of xi, right? If you're thinking about, for example, x2, the number of times that I make 2 free throws in 4 attempts, when I do 100 of those experiments, I think the probability of x2 occurring on any given run of 4 attempts was 0.3456 if I remember correctly. 100 times that, 34.56, approximately 35 or so, would be my expected number of times that I'd make 2 free throws in 4 attempts out of 100 trials. That's what that represents. Okay, it really is going back to a binomial formula there. This fraction and then added up, this has a chi-squared distribution with k minus 1 degrees of freedom. Here for us again, since we go from x0 to x4, k is actually 5, because I got 5 of those variables in that vector, and so I'd have 4 degrees of freedom. Here are the distributions of different chi-squared random variables. The green one here, that's actually the goldish one, the yellowish goldish one here, that's when there's 1 degree of freedom. The greenish one here, that's when there's 2 degrees of freedom. This teal colored one was when there's 3 degrees of freedom. So you can see as the degrees of freedom gets higher and higher, the distribution gets more spread out, has a bigger mean, a bigger standard deviation as well. Yeah, you can see the mean moving to the right too. So our case situation is again k equals 4 degrees of freedom. That's going to be this purple one is going to be the one that we're using here. So what happens in this experiment? Well, I need to make up some numbers here. Suppose after doing 100 of these experiments of 4 free throws each and counting how many successes I have, I get the observed vector, x, I'm using lowercase because it's an observed vector, which is x0, x1, x2, x3, and x4, is 8, 47, 32, 13, and 0. In 8 of the 100 trials, I make 0 out of 4 free throws. In 47 out of the 100 trials, I make 1 out of 4 free throws. In 32 of the 100, I make 2 out of 4. In 13 out of the 100, I make 3 out of 4. And woe is me, in 0 of the 100 do I make all 4. Okay? Note that the total number of successes overall here does match the original approach that I took with the original test that p was 0.4 versus the alternative that p was not 0.4. If you compute the total number of successes, 8 times 0 plus 47 times 1 plus 32 times 2 plus 13 times 3 plus 0 times 4, you do get 150. 150 successes out of 400. That was the 37.5% success rate, sample success rate. So it's matching that, but it is a different test, so I do get a different p-value and possibly a different decision to reject the null or not. What is the observed value of the chi-square statistic? Use the formula. Here it is. And in each case, notice I'm taking the observed minus expected quantity squared divided by expected. 8 minus 12.96 quantity squared divided by 12.96, that would be the observed value of the number of times I make 0, minus the expected number, which was 12.96 because the probability of making 0 was 0.1296, quantity squared divided by the expected. And I do that for each one of these. 47 minus 34.56 quantity squared divided by 34.56, etc. Take the time to compute these things, pause the video, come back. Did you get this? Hopefully I didn't make a mistake here. These are the values of each of those fractions. You add those up and you get the observed value of the chi-square statistic to be approximately 9.488. What is the corresponding p-value then if we use 4 degrees of freedom? I'm going to show you what it looks like in the table in the textbook that we use, and I'll also show you on a calculator. If you use the textbook, it's a little bit misleading. It seems that p is between 0.05 and 0.1, and if you use alpha as 0.05, you'd say we do not reject. But you will also notice that's very close to a boundary value in the table, and in fact, if you use technology, because of rounding, it doesn't match, and that's an amazing thing that happened. Using a calculator or a spreadsheet, you actually can find that p is technically slightly below 0.05. So this is right at the typical boundary of rejection. Really, this means you could decide whether to reject or not based on your personal opinion. You know, other times it's definitely more clear-cut one way or the other. If your teacher gives you an alpha, I guess you should go with that alpha, but this is, in real life, it's the boundary. So, and you should also realize that different observations that still correspond to 150 overall successes out of 400 attempts very well could lead to a different decision. There are different x vectors that could be made where the total number of successes is 150. That would result in a different chi-squared value and a different p-value. Let's take the time to look at both what you would get in a table from the book and also with a calculator, and then we'll also look at a spreadsheet here. So here's the way our table looks for the chi-squared distribution in our textbook that I use with my class. So we got 4 degrees of freedom here. The chi-square statistic, I already forgot what it was about 9.488. And if you go along the 4 degrees of freedom line here, look, you see a 9.49 there. So it makes it look like the right-tailed p-value is between 1 minus 0.9 and 1 minus 0.95, which would be between 5% and 10%. And it seems like we have a p-value bigger than 5%, ever so slightly, because it's 9.49 there. But that's rounding. If you use technology, either a calculator or a spreadsheet, you do end up seeing that it's actually less than 0.05. If on a TI calculator, for example, we go to the distribution menu and go down to chi-squared CDF and put 9.488 in there, 10 to the 99 for the upper, 4 degrees of freedom, and paste this, you get a number ever so slightly less than 0.05. And a spreadsheet will confirm that. We could do the chi-squared distribution function is actually the CDF, and so I'd have to do 1 minus that if I use this here. Again, the 9.488, I'm forgetting again, 9.488. Yes, that was the value of chi-squared. And how many degrees of freedom? Again, that's 4 degrees of freedom. I put a comma 4, and it is cumulative here. Since the chi-squared dist is the CDF, I have to do 1 minus that to get the area to the right. Yes, just barely less than 0.05. Chi dist by itself, I don't have to do 1 minus. I keep forgetting the chi-squared value here. Sorry about this. Oops. Let's forget this. 4.8 or 9.488, chi-dist 9.488 4 degrees of freedom gives the same answer. And chi-test, if I've got the tables in here of actual or observed values and an expected table as well, I can do that. I can highlight those numbers to get the same p-value, just barely less than 1. And you see it's slightly different here because of some rounding, evidently. I did some rounding in the PowerPoint as well. Okay, so yes, just barely less than 5%. According to the 5%, we'd want to reject the null, but since we're right at the boundary, that's still, slightly suspect. It's really a matter of opinion more. It's really a matter, if you want to get down to practicalities, of what are the effects of making a type 1 or type 2 error. If you reject the null, then you're subject to a type 1 error. The null could be true and you've rejected it. If you fail to reject, then you're subject to a type 2 error. The null would be false and you failed to reject it. What are the practical consequences of making an error like that? Since this is just free throws, my free throws, it really doesn't matter much. So it's more of a matter of opinion. All right, the other main topic for this lecture is testing for independence. So a study is conducted to test for independence, lack of association, and there's another way to say that, between air quality and air temperature. Observed data in a table I'm about to show you are obtained from 200 randomly selected days over the last few years. Do these data indicate an association between the variables? The null hypothesis is going to be that they're independent, that there's no association. The alternative will be that there is association. So if we reject the null, then we are saying yes, there is an association between these variables. Here's the data. So the temperatures are qualified or categorized, these are categorical variables, as below average, average, and above average. If you were using, the temp to the nearest degree in Celsius or Fahrenheit, it would just create this huge table. So it's simpler to separate it into categories, below average, average, and above average. And of course, with average, you'd probably have to say, within plus or minus 2 degrees of the average or something like that to really categorize this in a useful way. And the air quality is categorized as poor, fair, or good according to some standard of measure. And these numbers, the 1, 3, 24, 12, 28, 76, 12, 14, 30, are really the number of days out of these 200 days where the row category and the column category were satisfied. So there was only one day where the temp was both below average and the air quality was poor. There were 28 days where the temperature was average and the air quality was fair. There were 76 days where the temperature was close to average and the air quality was good. That's our observed data. And if you add up these numbers, you can double check that they add to 200. We want to fill in, to do this test, we want to fill in totals for the margins here. These are called marginal totals. And the notation is a little weird here. This is n sub 1 dot. That really adds up the numbers in row 1. The 1 there that's in the first spot is referring to the fact that we're in row 1. The dot means we're, that second number could be 1, 2, or 3 in a sense. This is just a placeholder. Add those numbers up. What would go over here? 1 plus 3 plus 24 would be 28. There would be a 28 that goes right here. And you could do that for the other row totals that are really giving you totals for temps. There were 28 days below average, for example. You could do the same for the quality of the air column totals. So for example, n sub dot 1 would be 1 plus 12 plus 12. There were 25 days where the air quality was poor. If you add up these totals or these totals, you will match the grand total of 200. And that's an important thing to do to help you finish the problem, to calculate the chi-square statistic. Here is the final table. You get, for example, the 28 here and the 25 here. The other numbers end up being 45 there, 130 here, 116 here, and 56. Add those numbers up to get 200. Add these numbers up to get 200. Okay, so this is the observed table. What we want to do now is we want to take these observed data and convert it to what's called an expected table. If you assume the null hypothesis is true, that there is no relationship between these variables. Now, just a cursory look at these data, by the way, indicates that there does seem to be a relationship. So for example, on below average temperature days, there are 24 times more good air quality days versus poor. On the other hand, on above average temperature days, Yes, the number of good days is higher than the number of poor days, but not by nearly as high a multiplier. Not by 24 times bigger, it's only on the order of 3 times bigger. So there does seem to be, in a basic look at these data, that we might reject the null. It seems like there is an association, but the question is, as always, is it statistically significant? What is the p-value? If there were no association between air quality and temperature, even though it seems like there is, in other words, if they were independent, then what would we expect? We would expect, for example, to be able to compute the average temperature days that have good air quality as the following. Expected number of average and good days, n sub 2, 3, meaning it's in row 2 and column 3 of the main body of the table, excluding the totals, columns, and rows, and excluding the labels. And what would that be? Well, just take the sample size, 200, and multiply times the probability of an average and good day. And if we're assuming the independence is true, that probability can be calculated with the multiplication rule for independent events as the probability of an average day times the probability of a good air quality day. Average temperature, good air quality. And those probabilities can be calculated as ratios. N2 dot over n that's the row total for the average temperature days divided by the total number of days, 200, times n dot 3 divided by n. This was the column total for column 3. Those were the good air quality days divided by the total sample size of 200 as well. We can cancel one of the n's and just have one n on the bottom and combine the numerators to get this quantity here as a shortcut way of calculating the expected number of days that were both average temperature and good air quality. That's really the row total, the second row total, times the third column total divided by n equals 200, the total sample size. And this can be generalized to say that the expected number in row I and column j of the main body of the table, which you denote EIJ hat means we're estimating something here, in the same kind of way, n sub I dot times n sub dot j divided by n. N sub I dot is the row total for row I, it's the number over here on the right in row I, and n sub dot j is the column total for column j, it's down at the bottom. And n is the total sample size, that's in the bottom right corner. So what you want to do is you want to compute these things, and in this case we're going to have 3 times 3, 9 computations like this to do to fill in a new table called the expected table right here. And I'll tell you that for my students in this book, you'll see in the book in the reading that the authors do not make a separate table. They put it in the original table with numbers in parentheses, but I'm going to make it a separate table. And here it is. Look at these computations. 28 times 25 divided by 200 is this row total times this column total divided by the grand total. And that turns out to be 3.5. Say this one, 116 times 45 over 200, that's this row total times this column total divided by the grand total. That turns out to be 26.1, etc. You can fill in all 9 of these spots in the main body of the table. It's a 3 times 3 table. 3 main rows, 3 main columns, if you exclude the labels in the total columns and rows. And from this, comparing the observed table and the expected table leads to the chi-squared statistic. You know, if our observations are far away from expected, that's going to mean ultimately the chi-squared statistic is going to be large, extreme, and that's going to result in a small p-value. We are observing something rare if the null is true, and that would lead to rejection of the null. But as usual, we need our test statistic, and like before, it's going to be a chi-squared statistic with a certain number of degrees of freedom and computed in a similar way. The corresponding sum of fractions, ratios, which are each fraction is squared observed minus expecteds as before, divided by expecteds, is once again approximately chi-squared, but this time the degrees of freedom is r minus 1 times c minus 1, where r is the number of rows in the main body of the table and c is the number of columns. R and c are both 3 for our example, so r minus 1 and c minus 1 are both 2 for our example, so we have 2 times 2 or 4 degrees of freedom for this example, just like before. It's traditional to write the chi-squared statistic as a double sum in this situation, though I should say you don't have to. The main thing you need to understand is that you are computing these fractions across all the entries in the main body of both tables at the same time effectively. Writing it as a double summation emphasizes that you can, for example, let I start at 1, start at row 1, and sum over all the columns in row 1 of these fractions. Then let I go up to 2, so you're looking at the second main row and you're summing across all the columns. And then let I be 3, etc., until I equals R. So you can more precisely write this as a double summation, but you don't have to. It's best to compute this with a spreadsheet, and we will here in a minute. But let's just get to the answers, and then we'll look at how to confirm that with the spreadsheet. For our example, here are the answers. The final answers are for chi-squared it's about 10.789, again with 4 degrees of freedom. What does that mean about the p-value? It ends up being a pretty small p-value. P is about 2.9%, less than the typical 5% level of significance, so that would typically be a decision to reject the null. Though you, again, in real life, you want to think about the practical meaning of either making a type 1 or type 2 error here. So if we reject the null, we'd be subject to at least the possibility of making a type 1 error of rejecting the null when it's true. What again is the null? The null is that there is no association between air quality and temperature, that they are independent of each other. If that's true, but we're rejecting it, we're saying there is an association. We're warning people, hey, if it's real hot out, especially if you've got asthma, don't go outside. The air quality is likely to be bad. So you'd be rejecting the null when it's actually true, when there actually is no association between air quality and temperature. So you'd be scaring people maybe more than you need to, though I'd want more data to be sure, to tell you the truth. On the other hand, making a type 2 error, which we are not subject to here, by the way, though if we were using alpha to be 1%, we would fail to reject and we would be subject to, is when you fail to reject the null when you should have, because it's false. The air quality really is affected by temperature, but you're saying it's not. Then people would be more likely to go outside even when it's warm and be subject to poor air quality when you're telling them there's no association. So there are practical things to think about here. Since if we use the 5% level, we're going to reject the null. We're going to say there is an association. They're not independent. Okay, let's end the video here, the lecture, by looking at the spreadsheet of how to do this computation efficiently on a spreadsheet. That it does involve some spreadsheet trickery involving fixed or absolute cell references. I'm not going to explain these much, but I'm assuming that you've seen this kind of thing before. So I did make an observed table. And from that observed table, I'd want to make an expected table. And by the way, these totals are in here, but I could have done them without those totals. I could have figured out those totals using formulas. For example, here I could have done sum across that first row equals sum, highlight those things, and that would be convenient to do, especially if the table were much bigger. And if I copy and paste that formula downward, I will sum across each one of those rows. And this total has a formula as well, equals sum F6 through F8, which I had done already. Then over here, I can sum across down these columns. I can go equals SUM C6 through C8 and copy and paste that formula over, or click and drag if you prefer. And then I want to make an expected table using that shortcut formula. This is a little tricky, especially if you want to use fixed cell references. I'd like to take, for example, for this spot, I'd like to take this row total in F6 times this column total in C9 and divide by F9, the 200. And I can do it with formulas. And if I want to copy and paste the formula to the right, I'd want to make sure that I keep this thing fixed, so use dollar signs, F6. I don't have to use them in both spots, but it is just as a default I'm going to. But do not keep C9 fixed. Do not use dollar signs there because I want that to change to becoming D9 and E9 as I copy and paste the formula across this row. Divide by 200, which is in F9. I do need to use dollar signs there, so that stays fixed. So 3.5, that is the expected number in the upper left corner. We saw that in the PowerPoint. Click and drag this over. I can also copy and paste the sum formula down here, and the sum is the same, 28. You can double check that these add to the same thing. I do need to update the formula for each row, so this is not as efficient as it could be. Here I take F7 as a fixed reference and C9 as a non-fixed reference and divide by F9 as a fixed reference and copy and paste that over to the right. Just click and drag. I can copy and paste this formula downward. There I get 116, just like that's 116 there. One more to do here. Take F8 times C9 without dollars divided by F9 again with dollar signs. Click and drag that over and take the sum on down as well. And yes, that's a 56. It matches the other 56. The total here is 200. I can copy and paste these formulas downward just to double check that they're the same, 25, 45, and 130. And now the quickest way to get the p-value is with chi-test. The actual range is that 3 by 3 matrix, and comma the expected range is this one. And this should give us the 2.9%, I think it was. Yes, 0.029. So that's the quickest way to get the p-value. You could theoretically get the p-value also from the formula for the chi-squared. It's not too bad here, and we can do some copying and pasting for the whole thing. We can do equals observed is in C6 minus expected in C14 divided quantity squared divided by expected, and do not use dollar signs here for fixed cell references because I want the copy and pasting to happen. This is not an observed or expected table. These are values that I get for each term in the chi-squared random variable. Now I can add those up. Maybe I should get rid of these total labels here so that's not confusing. Add those up. There's my chi-squared value, 10.789. 4 degrees of freedom. The p-value I can compute with, for example, equals chi-dist based on this chi-squared value and 4 degrees of freedom. So this should be 2.9% as well. And it is. Okay? So kind of tricky in some ways, but I definitely think you'll find it to be easier than multiple regression was. Thanks for watching.